Within our breakout session, it is my pleasure to welcome you to the session on compliance, evaluation and demonstration for HVDC grid and offshore wind farm controllers. My name is Philipp Ruffing and I'm working as team leader for the team DC systems at the RWTH Aachen University in Germany. Within promotion, my main responsibility was to lead work package 16. But in addition, I also helped doing the model development in Work Package 2, and I was responsible for the full bridge protection strategy in Work Package 2, as well as in Work Package 4. Before we dive into the detailed presentations, I will quickly give you an introduction on the topic itself, but also on the different presentations of today. So the main motivation behind the grid compliance evaluation and the demonstration about which we talk today is that meshed offshore DC systems lead to novel challenges for TSOs, for manufacturers, but also for grid planners. While today HVDC is mostly used for point-to-point connections, the increasing maturity of the technology, as well as the increasing need for operational flexibility, pushes HVDC towards multi-terminal applications and even towards HVDC grids in the future. First MTDC networks have now been built in China, and especially for the integration of our envisioned 450 gigawatts of offshore wind energy into the European transmission networks, HVDC is a key enabler. However, regardless of the technological, operational, or economic drivers behind HVDC networks, the experience regarding the operation of HVDC grids is still missing. This concerns, on the one hand, the multi-terminal operations, so the interactions between the HVDC converters themselves, the integration within large AC transmission systems or offshore wind farms, as well as the stability analysis in offshore networks. Based on the results of our technical work packages, so Work Package 2 on HVDC converter control algorithms, Work Package 3 on DRU-connected and black start capable wind power plants, as well as Work Package 4 on DC grid protection, it is our objective to demonstrate the operation of HVDC technologies beyond simulation. And therefore, we integrated partially commercial, partially academic wind turbine or small-scale HVDC converters, both in power hardware in the loop and control hardware in the loop test benches. And therefore, our high-level objectives are the demonstration of the developed control and simulation models, the technical de-risking for the deployment and the operation of offshore HVDC systems, and the improvement of the confidence on HVDC networks for rope wrapping processes and standardization efforts. Today's talk is separated into 3 sections. First of all, I will present our results on the demonstration of the controllability and the interoperability of offshore MTDC networks using a multi-terminal HVDC test bench. This is a power hardware in the loop demonstrator. And the investigations comprise the operation of different grid configurations, the interoperability between MTDC networks and offshore wind farms, the fault handling in HVDC grids, as well as a demonstration of the AC grid support concepts for offshore DC grids developed within the project. In the second part of our talk, Professor Ramon Blasco-Gimenez will give you some insights on the control hardware in the loop demonstration of offshore wind farms connected to shore via direct rectifier units and on the black start capability of offshore wind farms. The demonstration comprises, on the one hand, hardware wind turbine controllers and on the other hand, commercial protection hardware. And these are embedded into a real-time simulation test bench. Since offshore collector grids are 100% converter-driven networks without the damping characteristics of synchronous generators, for example, it is crucial to investigate their stability during an early stage of the corresponding project. Thus, during the third part of our presentation today, Dr. Yongtao Yang will guide you through the process on how to assess the stability in offshore collector grids. He will present how to characterize HVDC and wind turbine converters by measuring their frequency-dependent impedance characteristic and how to assess then, with these characteristics, the stability of the corresponding AC grid. I will now begin with our part on HVDC grid control demonstration. Since HVDC grids are complex and there are various challenges regarding the grid control but also the converter controllers, we defined a broad spectrum of test cases within the work package. Firstly, the controllability of HVDC grids in different network and circuit configurations using algorithms developed by Work Package 2. These had to be demonstrated. Moreover, we investigate the interoperability between offshore wind farms and HVDC grids, on the one hand using the HVDC converters to form the AC voltage of the collector network, but also using the wind turbine generators or the converters of the wind turbine generators of the wind power plants. Another aspect was the demonstration of the frequency support functions to AC transmission networks using, on the one hand, a communication-based approach, but also using a communication-less approach. Last but not least, we demonstrated different HVDC grid protection strategies. These were developed in our technical work package 4, and they include, on the one hand, a DC circuit breaker based strategy, a DC bypass concept, and the protection of HVDC grids based on fault blocking converters and low voltage and low energy DC circuit breakers. Within today's presentation, we will focus on the one hand of the interoperability of offshore wind power plants, and in this case using MMCs in grid forming function, and on the other hand on the protection strategy based on full bridge converters, so fault blocking converters, and low voltage, low energy DC circuit breakers. So for the purpose of these demonstrations, we built a small-scale HVDC grid demonstrator at the RWTH Aachen University over the course of the project, and this is called MMC Test Bench. At the core of the test bench, there are 8 laboratory-scaled modular multi-level converters with a power rating of 6 kilowatts and a nominal voltage of 400 volts. The MMCs are built similarly to HVDC grid converters. However, instead of having several hundred submodules, they only comprise 10 submodules per arm, which is completely sufficient for our test levels, however. The DC lines are represented using cascaded pi sections, and these are designed in a way to reflect a wide frequency spectrum. In total, we have 32 pi sections, and these are able to represent 800 kilometers of a bipolar grid or up to 1,600 kilometers of a monopolar grid. To integrate the test bench into the context of AC transmission systems and offshore collector grids, the MMCs are connected to a real-time simulator using linear 4-quadrant power amplifiers in a power hardware in the loop configuration. And this allows us to investigate and demonstrate the overall defined test cases within a laboratory scale. So this is how it looks like in the laboratory. So we have in total our 8 MMC converters. In the front, you will see the DC grid representation, so the cascaded pi sections. Then in the back, the 2 power amplifier or the 4 power amplifiers in total, and the real-time simulator rack, also with all the IOs. Overall, we can use the system in a power hardware or control hardware in the loop approach, and where in the power hardware loop approach, the DC grid is represented physically in the small scale, using the small scale representation. The AC transmission grids and offshore wind power plants, these are a real-time or embedded in a real-time simulation. If we use the control hardware in the loop approach, all the electrical parts, these are simulated in a real-time simulator, and the MMCs are simulated using an FPGA-based model, but we can use exactly the same controllers also for this real-time simulation, so the physical MMC controllers. And this is a very important aspect for us. So we have 3 test levels. On the first, at first, the MMC test bench itself, so the physical test, then a digital twin of the MMC test bench. So this is a lab-scaled model, partially also using the real converter controllers, and a full-scale simulation. So overall is the approach that these test levels match very well, so that the control is tested on the one hand for physical test, but on the other hand also for full-scale simulation tests. And as already introduced earlier, we will now start with the investigations and demonstration regarding the offshore wind farm integration using empty DC networks. And therefore, we'll use the 4-terminal monopolar promotion network, as you can see here, and the offshore wind power plants, so both wind power plant 1 and 2, as you can see here, are set up in a power hardware in the loop simulation, or in the power hardware in the loop test case. So in the end, the MMC converters, the HVDC converters, these are physical devices which are coupled or directly connected to a 4-quadrant power amplifier. And this power amplifier is controlled by using a real-time simulation of the collector grid, which is connected to a wind power plant controller or wind turbine controller. Overall, using this setup, we have been able to show that the energization of the offshore network can work properly, that the HVDC grid can be controlled in monopolar and bipolar configuration. And using this setup, we could show that, for example, during set point changes, but also during dynamic events, such as, for example, an outage of a wind power plant, there's a good matching between the physical tests and simulations. So you can see this here in the graph, for example, for the power flow of the offshore wind turbine. On the one hand, using the physical test bench converter in power hardware in the loop. Then a low-scale simulation in red, so this has exactly the same network rating, so plus minus 200 volts and 6 kilowatt per converter, and a full-scale simulation. And this full-scale simulation is then for a plus minus 320 kV network and 1.2 gigawatts per converter. Everything is scaled using a per unit scaling, and overall there is a quite good matching between the power flows here. So overall, the control concept, which was developed for controlling the offshore MMCs, this is has been tested here in different stages, and therefore the overall confidence in this control setup has been increased using this test case. So as already introduced regarding the protection demonstration of today, we will focus on the full bridge-based demonstration strategy. However, I quickly want to motivate why we look at this strategy and what is the background. So first of all, once it comes to HVDC grid protection, for sure it would be desirable to just install fast DC circuit breakers at each line end and treat every line as individual protection zone, so similar to AC grid protection system. In case of a fault, the DC voltage collapses and the current quickly rises. And in order to separate this fault, the circuit breakers at the faulted line ends, these have to separate under very high currents, and therefore also they have to absorb a lot of energy during this interruption process. So overall, the requirements on the DC switchgear are relatively high. An alternative approach is the protection of HVDC grids based on fault blocking converters. Here the entire grid is treated as one protection zone, and in the case of the fault, the DC voltage within the entire system collapses. All converters actively control their DC currents to zero, and thereby they stop to transfer energy from the AC into the DC system. After a short time, so several 10 milliseconds, this has been shown also in work package 4, the DC voltage, but also the current flowing through the DC switchgear, which shall separate the faulted line, these decay to values very close to zero, and thus the requirements on the DC switchgear are much reduced compared to full-size DC circuit breakers. For sure, after the fault separation, also the DC grid voltage has to be restored, and overall there's a high amount of coordination between the converters, the switchgear, and the overall grid control involved here. And due to this high complexity of the protection strategy, it is important to demonstrate that the DC fault controls of the fault blocking converters properly work in post-simulation, but also in the physical DC grid which we have built here, that the fault separation process itself and the communication or coordination between the MMC converters and the fault separation unit works properly, and that the DC grid voltage restoration commences after the overall fault separation process. So overall, there's a very high amount of coordination which is required here, and the objective of the demonstration is to increase the overall confidence in the protection strategy so that it can be applied also in future larger or future real HVDC grids. So for the purpose of this demonstration, we apply exactly the same HVDC grid as it has been used for the studies of work package 4. So here it's a monopolar HVDC grid based on 4 terminals, and on the one hand in work package 4 and also for the full-scale simulations, this is designed to fit plus minus 320 kV, and in the laboratory we operate this as plus minus 200 volts. All converters can communicate using a central DC grid controller, and the HVDC converters are represented using full-bit small-scale MMC converters, as already introduced earlier. The HVDC cables, these are represented using our cascaded pi sections, also designed for wider frequency range, and this allows us also to perform or to get a similar behavior within the small scale as within a full scale system, just using pi sections and not, for example, a universal line model. This we can for sure not use in our laboratory. The AC grids are represented using power amplifiers, and for these tests, the power amplifiers are only set into voltage source mode because the focus of the demonstration lies within the DC grid. For power hardware in the loop simulations, for example, there we would then use a simulation of a embedded AC grid, for example. The fault separation units, or also called residual current breakers, these are small-scale breakers designed by KTH, which have been applied here, and these are only allowed to interrupt once the current is relatively low, so below, I think, 10% around its nominal current. To be able to have to make a fault within the system, we had to build such a robust construction here, since the currents can be in the range of 200 to 300 amps, and therefore, if it's a smaller breaker, it might not be able to make the fault, at least to make it twice. And this is how it looks like. So let me now quickly guide you through the demonstration of an exemplary test case in a 4-terminal monopolar HVDC network, and the fault here is an exemplary fault in the middle of the line between station 3 and station 1. In the figure you can see the DC voltage as well as the DC current at station 1, and this on the one hand in blue for the MMC test bench measurement, then for the laboratory scale simulation and for the full scale simulation. And you can see overall in the first glance that the results match very well. So once a fault occurs, the DC voltage collapses on the positive pole. So this is the top pole. Yeah, this is the top pole, and the converters detect the fault and start to reduce their current flowing from the AC to the DC system to values close to zero very quickly. However, after the fault is located at this line, the converter station M1 switches into a so-called terminal voltage control mode, and this and the purpose for this is to quickly discharge the system in order to create near zero current as well as near zero voltage conditions for the residual current switch as fast as possible. And here, after around 40 milliseconds, the conditions are fulfilled and the residual current breaker can separate the faulted line. The restoration process is not displayed here, but overall we can conclude that in all our test cases the DC fault control worked in the demonstration as well as in the full-scale simulation. The coordination between the converters and the switchgear worked as planned, and also the grid restoration worked as foreseen in the studies from work package 4. So overall there's a very good matching between the simulation as well as our hardware demonstration. And to conclude this, the full bridge demonstration seems to be a very feasible solution for the protection of HVDC networks. With this, I would now like to conclude our results on the HVDC grid demonstration. First of all, the control and operation of multi-terminal HVDC grids is demonstrated on a test bench comprising downscaled MMC converters. Secondly, the interoperability between empty DC grids and offshore wind power plants on the one hand in grid following, on the other hand in grid forming mode, is demonstrated in the power hardware in the loop environment. And last but not least, the protection strategies, like for example the full bridge based HVDC grid protection strategy, but also the DC bypass switch concept, these are demonstrated, and it is shown that the proposed control methods that these enable robust fault right through operation. So with this, I would like to close this part of the presentation and hand over to Professor Ramon Blasco-Gimenez. Thank you very much.
Our next presentation deals with the control hardware in the loop validation of grid-forming wind turbine controllers, first for black start operation with offshore wind farms, and second for the connection of offshore wind farms to diode rectifier HVDC links. My name is Ramon Blasco-Gimenez, and I'm a professor with the Technical University of Valencia in Spain. We've been working for about 15 years on wind turbine grid forming control for both HVDC and HVAC integration. Within the promotion project, we've been working in 4 work packages on the development and validation of wind turbine grid forming controllers for diode rectifier connected wind farms, and also for black start and islanding operation. This is the system we use for control hardware in the loop validation, where we have 13 PWM back-to-back converters per wind farm. We have up to 3 wind farms. We also have a full MMC link with the corresponding valve and pole controls for HVDC studies, together with a wind power plant controller and a number of DSP-based converter controllers connected by means of an Ethercat network. We also have a process bus for the connection of protection relays and a power amplifier for eventual connection to actor power hardware in the loop systems. In the first part of the presentation, we'll show the validation of grid-forming wind turbine controllers for black start operation. Our main aim has been to increase the TRL of the grid-forming controllers. In the initial work packages 2 and 3, we defined the functional requirements for such controllers, the scenarios, both for HVDC and HVAC connected wind farms, the test cases, and finally we carried out the validation of different controllers by means of detailed simulations. Once we finished with the validation using simulations, we moved into work package 16, where we carried out the validation based on real-time simulations. Our colleagues at DNVGL carried out both control hardware in the loop and power hardware in the loop validation of a single wind turbine generator. And at the Technical University of Valencia, we carried out the control hardware in the loop validation considering multiple wind turbines and also system protection. The scenario we've considered for black start operation is a 400 megawatt wind farm consisting of 50 wind turbines of 8 megawatts each and located 75 kilometers away from the onshore HVAC substation. The connection process starts by a single wind turbine energizing the first string cable, then the rest of the wind turbines of that string. Then we will have enough reactive power to energize the whole array, followed by the rest of the wind turbines. At this stage, the whole system will be operating in an island. And then we will energize the offshore substation, the HVAC export cable, and the onshore substation. So once we have the onshore substation energized, we can actually power up local block loads and finally connect to adjacent islands just to continue with the surface restoration process. The main issues are HVAC cable and transformer energization, response to load transients, and fault response and fault recovery. Here you can see some results. On the left, you have the export cable energization. This is directly connected. You see the voltage seen by the wind turbine, the current seen by the wind turbines, and the offshore collector busbar voltage and currents. And you see that the direct connection is causing quite a lot of harmonics and resonance between the transformer and the cable. The alternative, you can see it on the right, where we perform the soft start, where all the wind turbines are synchronized with a relatively low voltage. All the switches down to the onshore grid are closed, and then the voltage of all the wind turbines are ramped up. That can be done relatively quickly, as we don't have this kind of resonances, and obviously we avoid over voltages and over currents. These results show the operation of the wind farm during an export cable fault. The first two traces show the voltage and current of one of the wind turbines, and the bottom two, the voltage and current at the offshore collector bus bars. The grid-forming wind turbines keep the current control during the fault, and once the fault is cleared, The wind turbines will recover the system voltage in about 50 milliseconds. This is an important behavior, as now the wind turbines are the only grid-forming equipment in the system, and therefore are in charge of voltage recovery after the fault. The previous results are just a small portion of the tests that we carried out. The main lessons to learn is that the real-time simulation must have a sufficient number of wind turbines, so the resonances and interactions between the wind turbines are identified at a very early stage. Sequential black start is possible, but it might lead to overvoltages and overcurrents, which could trip the wind turbines in some cases, so detailed studies are needed if sequential black start is got to be used. On the other hand, soft start leads to much faster energization and very small inrush currents and oscillations. Finally, fault response and fault recovery coordination is extremely important when we have a very large number of grid-forming wind turbines. The main conclusion is that grid-forming wind power plants can contribute to a substantial reduction on service restoration time after a blackout. For the second part of the presentation, I'm going to show the control hardware in the loop validation of DRU-connected wind turbine controllers. First of all, we have to consider the functional requirements for DRU operation that were defined earlier in the project and that have been used also for the validation using offline simulations. Those requirements are very detailed and include both islanding operation and synchronized operation to the onshore HVAC grid. The system we have considered for the control hardware in the loop validation consists of 3 offshore wind farms of 400 megawatts each. For the modeling of each individual wind turbines, the full back-to-back converters with PWM and also with the mechanical subsystems and the aerodynamical subsystems have been included. And to be able to simulate all the system in real time, we have included a detailed string with 9 wind turbines of 8 megawatts each, then 5 aggregated strings, and then finally 2 wind farms as aggregated wind turbines. Then we include 3 diode rectifier platforms, including all the breakers and AC filters, and connected in series on their DC side. Finally, the MMC converter is based on half-bridge modules with a total of 401 levels, and the MMC converter is totally simulated on an FPGA. The controllers that have been used for testing the complete system are based on PVQ omega groups. They have internal voltage and current loops, and the machine side converter control is the same as that has been done for the black start operation and is in charge of keeping constant the DC link voltage. The power up of the whole system is being carried out either using an umbilical HVAC cable or using local energy storage in each one of the wind turbines. The complete verification of all the wind turbine controllers include a very large number of test cases. We are including here only some examples, so you can see the functionality of the complete system. So one of the first examples we see here is the operation when we connect the diode rectifier AC filter banks, and then when we ramp up to full power production. So you see in these graphs the voltage on the first wind turbine, the current out of this first wind turbine, and also the active and reactive power out of each one of the wind turbines of the system. So you can see that at T equals 0.1 seconds, the filters are connected, and then the power generation is ramped up and full power is reached in about 200, 300 milliseconds. This is a very large ramping rate, which is shown there just to prove that the system is operating correctly, but in actual situation, the actual ramping up of the delivered power will be much slower. The offshore AC voltage is quickly recovered, and active power production is resumed in less than 50 milliseconds. This example shows the operation during faults. In this case, during faults on the offshore AC grid, again we see the top trace is the voltage on one of the wind turbines. The second is the current of that wind turbine, and the other two traces are the active and reactive power out of each one of the individual wind turbines. We see that at t equals 0.1 second, there's a fault, and that fault lasts for about 200 milliseconds. After the fault is being cleared, we have carried out the control hardware in the loop validation of diode rectifier enabled grid-forming wind turbine controllers. We have considered all the functional requirements for the different modes of operation, both in islanding and in HVAC synchronized, and the transition between the operational modes, and also the fault response to faults in different parts of the system. Something that is very important is to consider a sufficiently large number of wind turbine generators. Otherwise, it is possible to miss interactions between the wind turbines. Finally, it is worth stressing that fault response and fault recovery can be particularly challenging with a very large number of grid-forming converters. The main conclusion is that we have carried out a control hardware in the loop detailed validation of wind turbine grid-forming controllers for black start and for DRU operation, and therefore we have increased the TRL of such controllers. Thanks a lot for your attention, and I'll be happy to answer any questions you may have.
Hello. In this session, we were talking about the stability assessment using the tool test bench as described by Philipp. My name is Yongtao Yang. I'm working as a principal consultant in the energy market and technology team in DNVGL in Oslo, Norway. In the promotion project, I've been working in a few work packages. Among others, in work packages 16, I'm working on the control hardware in the loop and power hardware in the loop testing of wind turbine converters and MMC VSC converters. I'm also working in work package 12, leading the task force for collecting cost data for the offshore power transmission system. And also working in worker package 2 and 4, supporting the DC grid modeling and protection system design. The background of this assessment, as we knew that with the increased penetration of power electronic device, they shows across a new category of instability. That's harmonic instability. That's the sustained oscillation in such a converter-dominated networks. This is going to be shown in the diagram to the right. Here in this analysis, we use frequency domain analysis to address this instability. For example, in this diagram shown here with a wind turbine converter connected with HVDC converter, we model the system as two subsystems have frequency dependent impedance and also the corresponding current source and the voltage source. The stability of the overall system it's analyzed by the open loop gain G0 of the system. We say the system is stable if G0 defined by impedance of MMC divided by impedance of wind turbine converter satisfy the so-called Nyquist stability criteria. In this implementation, we actually even more simplified that to the so-called Borkhausen stability criteria. Basically, we say that the system is stable as long as G0 is not equal to -1. Furthermore, we could say that the system is unstable if the absolute value of these two impedances is equal to each other, and the phase angle of those, the sum of the phase angle is equal to pi. So all it's needed for this assessment is actually the two impedance, which will be done by impedance measurement. In this, we show a bit of overall step you might need to perform such a stability assessment using frequency domain assessment. Which first you could do a analytic derivation of the input impedance, and then based on the analytic expression, you could selection and development of accurate method for the measurement. Then we measure the input impedance of relevant converter. In our problem, so it will be both wind turbines and HVDC converters. And then we assess the stability in the frequency domain. That's essentially using Nyquist or Borkhausen stability criteria. And the last part, we validate the results in the time domain. So here we have performed both. One is in PSCAT time domain simulation. The other one is in with a real-time digital simulation using controller hardware in the loop. I put it in the parentheses because we are, due to different logistic challenges, we are not able to perform the full assessment. But still show you the setup. So the measurement for the wind turbine generator impedance is showed as below. So as we perform the both to the left, you see a controller hardware in the loop test setup. So here you show the real controller replica from the OEM, and to the top you see the wind turbine primary component and the power grid implement in the real-time simulation digital simulators. This is the controller hardware in the loop testing. To the right, we show a diagram of a power hardware in the loop testing. So this is the real actually the 1 megawatt wind turbine converter. And the system is perturbed by a harmonic sources with different harmonic at different frequencies, and to perturbate the system, and we measure the voltage and the current at the terminal. This is the lab picture. The white cabinet is actually hosts the converters, the 1 megawatt converters for the wind turbine. In these slides, we show the test bench, the MMC test bench for the impedance measurement. So as you see that this MMC1 converter is perturbed, and it depends on different. You have a different perturbation, voltage perturbation if this running in a grid following model, and it will be perturbed as a current if it is in a grid forming control model. And then we measure the voltage and current, and then they essentially go through the digital Fourier transformation to essentially to get the the frequency in the impedance in frequency domain. This is a show for essentially the power with the power amplifier. That's the test bench, and equally we can also do it in a digital twin. So that means it's only the controller replicas in the test loop. In this slide, we show the impedance measurement results of the wind turbine generator as we perform the measurement in a DQ frame. So we have a 2x2 complex matrix as the impedance, as shown in here. We compare the power hardware in the loop, controller hardware in the loop, and PSCAD calculation results. As you can see, until medium frequency range, there are all of three has a good agreement with each other. Beyond the medium frequency range, the power hardware in the loop testing has suffered from noise and stability issues, so that they deviate quite a bit. And then in the 2x2 matrix, ZDD is actually representing the characteristic of a DC link. The ZDD and the ZQQ is actually the phase lock loop characteristics, which is very often has a with very often showed up in the medium frequency range oscillation. The diagonal component is actually the current loop, control loop representation. In this slide, we show the assessment with AC grid and grid following MMC, as circled by the red squares. So we assess for we vary the grid strength of the AC grid, the so-called short circuit ratio, and then as you can see here, the blue curve is actually the MMC's frequent impedance, and then there are a few different colors showing the grid impedance representing different short circuit ratio. And if we enlarge this section, we can see that at this when SCR equal to 4, we have the two impedance has the same magnitude, and the sum of their phase angle is close to pi, 180 degrees. So that's we identify as a close to a unstable system. Here we show the time domain validation of this. You can show this is the spectrum. We do the simulation, and then we continuously step by step reduce the SCR of the AC grid. We see from when changing from 5 to 4, this oscillation happened. You can see a bit more clear in this diagram. You can see the oscillation, and also the frequency domain analysis. So clearly show this oscillation happened at 94.5. close to 100 Hertz. The next slides we show the stability assessment of the grid forming MMC and wind farm, as surrounded by this red square here. This is the offshore wind farm. It's showed like this, and we change the layout of them in a different combination. Here show the MMC and the wind farm impedance, and this is the magnitude, and this is the phase angle. We can see that at the we can identify a unstable situation, or stable with a lower stability margin at around 11,000 hertz, 1100 hertz, where we see the magnitude is almost the same, and the sum of the phase angle approaching 180 degrees. So that's you have a lower stability margin issue. In this slide, we show the converter hardware in the loop testing bench for MMC VAC HVDC connected to a offshore wind. The dimension of the system is 1,200 megawatt plus minus 320 kV. So the system, the primary system is modeled in the OPO-RT HyperSim system. They are connected with the OPO system with extension box to connecting the IOs. The offshore converter station and onshore converter station was actually simulated through a group of controller replicas from a vendor. And they are connected through to the OPO system through digital and analog and fiber optics signals. Further on, the offshore wind farm is actually represented by the wind turbine controller replicas. As I said before, we didn't manage to run the time domain validation of the harmonic stability assessment. We only managed to run a few simple tests. So these slides show the fault right through of this system. To the left, you show the offshore converter station. To the right is the onshore, and at the top being the current voltage and DC voltage, active power and a reactive power of the two converter station. Here we run at 0.2 second. We have a three-phase to ground failure, and then of course the active power go to 0, but for the offshore it's continual injection, so that the DC voltage rise due to the surplus in active power, and this was was mitigated by the DC chopper in the system to prevent the voltage rising too high. After 200 milliseconds, the fault was cleared, and then the system goes back to the normal operation. To recapture this session, we have demonstrated the method to measure the frequency response of wind turbine generator and the laboratory scale MMC converters. And we also demonstrate the control hardware in the loop test benching using controller replicas of wind turbine generator and MMC VSC converter from vendors. The frequency domain analysis enables us to effectively assess harmonic stability. Even if you have system components that are owned from a different partner, there's no internal knowledge needed about the converter to be shared among the partners. The instability we predict the instability and verify them in the time domain simulation for the onshore system with a moderate short circuit ratio. Thank you.
Thank you very much, Ramon and Yongtao, for your presentations. And before we close this part of our technical breakout session today, so our part on HVDC grid control and offshore wind farm control, I would like to thank everyone from WP16 who actively contributed to generating these results. Moreover, you will find more information about the work package and the work of which was presented today on our website, and in particular we recorded 2 demos. So one demonstration on the HVDC control and protection using the laboratory test bench you have seen today, as well as a demonstration on the control hardware in the loop environment for the offshore wind power plants, so the grid forming offshore wind power plant demonstrations. Moreover, we will submit and we will publish our final deliverable, D16.4, very soon. So this will be available end of September, and there you will be able to find all the test case analysis and all the detailed information about the results from our work package, which you have seen in a very broad overview today. So with this said, thank you very much for your attention, and if there are any further questions, please do not hesitate to contact us.